Hello, how you doing? Welcome back. This is my second video on logarithms, okay? If this is my first one, it's all about graphs and where the logarithmic graph comes from. This video introduces logarithms from a different perspective, okay? First of all, John Napier, Scottish mathematician, he's the one who actually came up with the idea of logarithms. What's it all about? Well, you know about exponentials. This is an exponential expression, e to the power of x, a to the power of x, 2 to the power of x. Anything to the power of x is basically an exponential function, okay? Here we've got 2 to the power of x, and we call that base number 2. The inverse of that expression would be log base 2 of x, okay? So logarithms are actually the inverse of an exponential function. Now, we need to know what the key terms are. We call this a power, or an index, or an exponent, okay? Any of those will do, but because it's exponentials and logarithms, I'm going to call that the exponent, okay? This 2 is the base number. That's important, okay? Because when you're taking logarithms, you can use different bases. Now, if this is base 2 for the exponential, then the inverse of that as a logarithm will be base 2 as well, log base 2. And the base we write just like that, okay? So these two are expressions that are inverses of each other. So log base 2 of x is an inverse of 2 to the power of x and vice versa. Okay? That's what logarithm is all about the inverse function of an exponential. Right, moving on, more generally, we use a to the power of x, where a can be any number within reason, okay? When I say within reason, generally I like to introduce this using positive integers. A cannot be 1 in this instance. Mainly 1 to the power of x is just 1. We don't have a base number of 1 when we deal with logarithms. Also, a is not 0. We don't talk about a base of 0. And we don't have negative values. I say any number, any positive integer is what I'm using. I can have fractional values, yes, but it's just going to be simple in my video if I talk about any positive value. But anyway, that's our generic base value of a to the power of x. And the inverse of that then will be log base a of x. Some important results that are probably worth writing down, okay, because they come up reasonably often. Now, because of your knowledge of powers and how exponents work, I'm hoping these are fairly obvious to you. A to the power of 1 equals a, and a to the 0 is equal to 1. Just bear in mind what I said about certain values of a. We're not using a as 0 for these cases, okay? And generally speaking, when we're doing logarithms, we don't use a base of 1 either, okay? But it follows that these two are true as well. Log base a of a is 1, and log base a of 1 is equal to 0. The last two are easier to spot, because if you've seen my graph video on exponential logarithms, you'll recall it looks like this. There's the exponential graph. If we reflect that through the line y equals x, we get the inverse function. That's how inverses work, of y equals log base a of x. This is a one-to-one function, so we're absolutely fine with finding an inverse. Notice the y-intercept there. That is because a to the power of 0 is 1, where we assume a is a number like 2 or 5, or simple number like that. Okay. Similarly then, when you find the inverse, the x-intercept is also going to be 1. So 1, 0 is where the logarithm graph will pass through. And that is no matter what base number you have, you're always going to have the log of 1 is equal to 0. So that's that, okay? Now, moving onwards. Here we go. Here's just some examples of how exponentials and logarithms look as inverses of each other. So I've got a table here. Over here, I've got some expressions using exponentials. Over here, some expressions using logarithms, okay? This is the inverse of this. This is the inverse of this. This is the inverse of this, and vice versa. Okay? These aren't questions for you to do or to work out. I'm just showing you examples of what the inverses look like. Okay? So I just chose that one there. That says y equals 10 to the power of x. The inverse function of that is this one here, y equals log base 10 of x. See how this works? You need to know the base number, so 2 or 3 or 10 or any other base. And then the inverse of an exponential will be a logarithm, same base. So same base of 2, 3, and 10. Okay? That's essentially your introduction to logarithms and what they are. It's useful to be able to rewrite expressions from exponential form to logarithm form and vice versa. I'll give you some examples of how that works. Okay? So 2 to the power 5 is 32. What I've done is I've just chosen simple numbers and written down an exponential equivalency. Okay, so 2 to the power 5, you know that 2 to the power 5 is 32. Okay, so that's a correct statement. A correct logarithmic statement looks like this. Now, how do we get from one to the other? Well, first of all, I'm after an inverse, so it's got to be a logarithm. I'm dealing with base 2 for my exponential, so I'm going to have to deal with base 2 for my logarithm. Okay, so it's going to be log base 2 of something. Now, the next bit, try and think about how you would find an inverse operation, an inverse function, okay, like you're trying to solve an equation. Okay, the inverse operation of 2 to the power 5 is log base 2, but what we're doing is we're effectively applying that to both sides of this. Okay, both sides of this. It's not really an equation because there's nothing to work out. More of an identity if you want, okay? We're working out the inverse of both the left and the right hand side. Let me rephrase it and put it a different way, okay? Start off with the number 5. Now I want you to do 2 to the power of that number and then reverse the operation. You're back to the number 5, okay? Suppose I ask you to do something slightly different. Start with the number 5, multiply it by 7, now do the inverse operation. Divide by 7, of course. You're back to the same number 5. That's what's going on here, okay? By applying this inverse of this, we're getting back to the number 5. See how that works? So we're left with 5 is equal to, and it's log base 2 of 32. I've just written it this way around because I want the log term to be on the left, okay? I'll do a few more of these. So here, another exponential expression here, 10 to the power 4, it's 10,000, okay, obviously. Can you think of a logarithm expression that would go with this? Now, if you want, you just pause the video and have a think, and then unpause it, and then see what the solution is, okay? Well, base is 10, so we want to be using log base 10, don't we, okay? And because it says 10 to the power 4 equals 10,000, the inverse operation of log 10 to the power 4 is log base 10. So what we're left with is 4 is equal to log base 10 of 10,000. All right, did you get that? Let's do another one. So again, pause the video if you want to have a think about it. This says 7 to the power 3 equals 343. The base number is 7, so I'm going to have log base 7. See how easy it is? So I'm going to apply log base 7 to both sides. I'm going to phrase it like that this time. Applying that to both sides, you've got log base 7 of 343, and you're just left with number 3 on the left-hand side, okay? Let me just use the example I used earlier. Start with the number 3. Now do 7 to the power of that number. Now do the inverse of what you just did. You're back to the number 3 again. Okay, and that's how this is working. Okay, I'm hoping that makes a lot of sense to you. Incidentally, before I go to the next page, when you're using base 10, there's no requirement to write down the base number, and that is the only exception in these cases I'm talking about. Okay, so when it's a base of 2 or 7 or 5 or any other base, you are required to write down the base number. But the notation in mathematics is when it's log, log, you don't need to write the base 10. Some people just abbreviate it to this, LG. I don't really do that. I don't like those things, okay? LG, life's good, okay? Bit of advertisement there for the TV brand, okay? Sorry, this is not an LG board. But yeah, but I tend to use LOG, 10,000. Right, let's have a look at some more. In more general terms, when you've got log base A of n is equal to x, an inverse inverse expression for that would be the n exponential of base A. So log base A means it's going to be base A, so a to the power of x is equal to n. See how that works? Now this time what I'm doing is I'm saying start off with number n, do a logarithm of that number, now do the inverse, you're back to n again, all right? And that's why you just got n is equal to a to the power of x. Now this way round is asked you to think about an equivalent exponential equivalency, okay? So log base 5 of 625 is equal to 4. Try and think about what an exponential expression would be. Again, pause the video, have a think about it. Did you come up with this? I'm hoping so. Basically, you've got base 5 for the logarithm. So when you're choosing your exponential, it's got to be 5 to the power of something. And I hope you're getting the idea. It's just be 5 to the power of 4. and then is equal to 625. Now here's the thing, these are easy to check, these less so, okay, but these are easy to check because you can quickly do 5 to the power 4 in your head and reason that it's going to be, that looks about right, 625, and of course it is. So you can actually check these answers. So what you could do is you could just take a guess and see what it's like. I really don't like people guessing, but if this is the last resort, then do that, okay? As long as you've got the right base number, 2, so you start with 2 to the power of. Now, can you put the numbers 256 and 8 somewhere to get the right thing? I'm hoping it's not 2 to the power of 256. That's preposterous, that's not equal to 8. But 2 to the power of 8, that does seem reasonable, it's 256. And indeed it is. Mathematically, what's going on, of course, is you're using the base of 2 for your exponential form, 2 to the power of something, and then you're doing 2 to the power of 8, and you're doing 2 to the power of this. We don't write this, okay? We don't write 2 to the power of log base 2 of 256, okay? But really, mathematically, that's what's going on, okay? We're doing 2 to the power of on both sides. It's just that these two, because they're self-inverses of each other, they're effectively cancelling each other out. You're left with the 256. That's what's going on there, okay? And is there another one? Yes, there is. One more. Have a go at that one. Done. Good. There we go. So base is 6. 6 to the power of 2. 6 squared. And of course that is 36. Now you can use your calculator to check these. Okay, using your calculator, you should be able to just type this in. Okay. If your calculator does not allow you to change the base to a 5, then I'll talk about that a little bit later. Okay. But all calculators, all modern calculators, should now have the ability for you to type in the base. So you should be able to type in log and then enter the base number you want, and then this value here, and then press the equals button. It should give you answer 4. So you can actually check these in your calculator. Maybe actually pause the video and do that. If you've not actually used your calculator for working out logarithms before, just do that to check you can. These are the answers, so just type this in, you should get the answer of 8. Just type this in, you should get the answer of 2. I'm hoping that goes well for you, okay? Right, next up, how do we do these? Okay, so at some point you might solve an equation and get that as an answer, and you want to work out what that is, log base 3 of 81. Now, as I've just said, if you've got a calculator that allows you to just type this in, then great, you can actually do that. Okay, you just type in log base 3 of 81 and you should get your answer. Okay, but what if you can't do that? Okay, this is what you do, this is your method. You first of all set it up as an equation where you let x is equal to log base 3 of 81, and then you find an equivalent exponential equation form to write in. Bear in mind that's base 3, so you'd rewrite that as 3 to the power of x, just like we did in the previous examples. Okay, so 3 to the power of x equals 81, and then you can work out what it is. You should know that 3 to the power of 4 is equal to 81, and so x is equal to 4. But if you type that in your calculator, it'll give you the answer straight away. Alright, this one here, maybe pause the video and do the same again. Unpause it, good, or maybe just continue to watch this. Okay, so set it up as an equation, and you try and work out x is. So x is log base 4 0.25. Then do the inverse of both sides. Inverse of log base 4 is 4 to the power of. So you know the 4 to the power of x is equal to 0.25. Now I'm hoping you recognise that 0.25 is 1/4. Or it's 4 to the power of -1. All right, and so 4 to the power of -1 is 1/4, and so quite simply, you just got your answer. X is equal to -1. Okay, and that's all there is to it. Right, next, how do you find the value of this? Well, I've not given you a base number there, have you? Have I? What you could do is just test it out. Okay, just choose a value of a, like 5 or 2 or 10, and just see what actually happens. Okay, but how do you actually do it? I'll start you off, just do the same as what we did before. Maybe pause the video again and have a go at it. I've written it as x equals something. Now what I'm going to do is do the inverse operation of log base a, which is a to the power of. So a to the power of x is equal to a to the power of 7. Can you see how easy this is? The base numbers are the same, a and a. It's just the exponents, the indices, the powers must be equal. X must be 7. Okay, and that's it. Right, next, find the value of x which satisfies these. All right, 10 to the power of x equals 500. Now, so far, the examples I've given you have been lovely values to work with. integers or fractions, something that's workable, something you can do without a calculator, okay? But this one is just a little bit different, okay? You're going to find the value of x that makes 10 to the power of x equals 500. Now, if you're in a lower year group, or maybe year 7, year 8, year 9, even year 10, year 11, if you've not seen logarithms, you might just use trial and error. So you know that 10 squared is 100, 10 cubed is 1,000. So go for somewhere between 2 and 3, do 10 to the power of 2.5, and keep using your calculator until you get close to the value of 500, and then round it to the appropriate degree of accuracy. With this, we can use logarithms. Okay, we can use logarithms to do it. So our first step is just do the inverse of 10 to the power of to both sides. The inverse of 10 to the power of is log base 10. So your x equals log base 10 of 500. And then you just type it in. Okay? And you get your answer 2.70. I've rounded it to 3 significant figures for this one. Give a go at that one. Maybe pause the video, have a go at it. Maybe I could have made it a bit harder. I've given the same base number, of course, 10, so that makes it pretty easy, okay? But I don't want to make it too difficult. I want to just keep things nice and simple. So just do the same again. You do the inverse operation of 10 to the power of, which is log base 10. So you just have, oops, there it is, log base 10 of 2,400, okay, which is 3.38. All right. Now, that's my introduction to logarithms without using graphs. If you've seen a bit of logarithms already, I'm hoping you're thinking there are other ways of solving these problems, okay? But notice I've not talked about the laws of logarithms yet, all the log laws that you might have written down in the piece. I've not used any of those, okay? So if you're wondering why I've not used a power rule here or why I've not used a multiplication rule here, it's because this video is not about that. This is just simply an introduction to logarithms, making you feel more comfortable with logarithmic expressions and what they're all about, okay? I'm hoping that this has done something for you. I'm hoping that you're feeling a bit more comfortable with logarithms now, okay? But my next video that I do will be about using the laws of logarithms, okay? Can't wait? Well, watch it straight away then, okay? Watch it straight away. I'm gonna have a cup of tea first though. See you soon.